Welcome to Easy Tech. I am Nawaz. I'll be dealing with the structure analysis 1. In this video, we're going to learn about degree of kinematic indeterminacy. So this is the outline of the video. First, we'll study about the degree of freedom. Then we'll study about see about the degree of kinematic indeterminacy for beams, frames, and trusses. So before entering into the degree of kinematic indeterminacy, let us understand the joint of a beam. So we all know that beam has two parts. One is joint and another is member. So member comprises of two joints. So in the softwares we deal with this one as a node and this one as node, this one as member. Now when we model a joint, and if we have a joint, it is free to rotate, free to move in any directions. If we consider the two structures, suppose we take a joint here, it is in the 2D, it is free to move in x direction, it is free to move in y direction, and it is free to rotate in with respect to this z direction. So these are the main principal movements in 2D structures a node can move. Okay. This is the basic to find out the degree of kinematic indeterminacy. Now let us see about the degree of freedom. So in the previous video we have studied about this rollers, different type of supports. So we have seen a roller support have one reaction. So what does this roller support does is, it will, suppose if there is a beam or node here, this is a node or a joint, it is continuing to beam, it is connected to a member. Okay. So what does this roller support does is, it will prevent the node to move in vertical direction, causing a reaction. So this roller support will prevent the movement in vertical direction, whereas it is free to move in x direction, as well as it is free to move with respect to this point. So here in this image you can see, so it is free, it can displace in x direction and it can free to rotate. It is in initial position, is free to rotate it with respect to the roller's point. Similarly, for pinned support also, we studied that it has two reactions, that is horizontal reaction, vertical reaction. So what does this pin do is, it will prevent, if we assume the node is here and is connected to it, it will prevent the movement in x direction and y direction, causing reactions, but it is free to rotate with respect to point. So here you can see this will be your initial position and it is free to move with respect to this pin point. Whereas for fixed support, since it is restraining or preventing the node, if you assume this is a node and this is connected to a member, it is preventing the node to move in any of the directions. So horizontal direction, vertical direction with respect to rotation. Since it is preventing, here it won't move, the node or member won't move when it is having a fixed support. The number of directions a node is free to move or a support is free to move is known as degree of freedom. In the roller case, the node is free to move in horizontal direction and it is free to rotate in rotation direction. It is the degree of freedom, we usually call this one as df. The degree of freedom of the roller support is 2. Whereas for pinned support, since it is only allowing the node to rotate with respect to z direction, so the degree of freedom for the pinned support is 1. Whereas for fixed support, it is preventing the node in any direction, so the degree of freedom of the fixed support is 0. This is everything about this degree of freedom. Let us see, consider a fixed beam. So we already have seen that fixed end beam, where the both ends of the beam are fixed. So we'll get these three reactions on one end and another three reactions in the other end. Now we have already also seen first video that it is statically indeterminate beam and the degree of static indeterminacy is 3. But when we come to the kinematic indeterminacy, the degree of indeterminacy here, this will prevent any movement. So there is the degree of freedom of at this end is 0, the degree of freedom at this end is 0. So the sum of these two will give the degree of kinematic indeterminacy. So the dk will be equal to 0. And another way to find out is using this formula. So this formula is applicable. This formula is applicable throughout the beams as well as frames too. So when we substitute these values in this formula, we'll get the degree of kinematic indeterminacy. That is, J here indicates number of joints. And R indicates number of reactions. Is a shortcut for reactions. So now when we substitute how many joints we have here, so we have only one beam, one member, and one member has two joints as we already have seen. So substituting the two joints here, and how many number of reactions I am getting here? So the total number of reactions I am getting is 6. I substitute that. So 3 2 just 6, 6 minus 6 equal to 0. So this is kinematically determinate beam, whereas it is statically indeterminate. So what is the need of studying these two is, here in the statically indeterminacy, what we'll do is we'll consider the number of reactions as input. We are trying to find out how many number of reactions, to find out the number of reactions or the magnitude of reactions. Whereas in the degree of kinematic indeterminacy, we are not at all bothered about the reactions, but instead we'll start with finding out the displacements and rotations. So here that's what we are taking. We are taking at each node we have 3 degrees of freedom, right? So at each node we have 3 degrees of freedom. If we just consider a joint, and from that we are subtracting the number of reactions. Right? So here we will get 3 degrees of freedom, but due to the fixed conditions, we are getting it is preventing we are getting 3 reactions. Similarly, here also we have 3 degrees of freedom, but due to the fixed end, we are getting 3 reactions. So both will get cancelled. This gives me 0. So this is degree of this is kinematically determinate beam, and if we are trying to find out solve using displacement method, this is the easiest way to solve this problem. We'll see that in the coming sessions. So now let us say simply supported beam, which is statically determinate. So we already seen the number of equilibrium equations are 3. This is the statically determinate beam. Why? Because the degree of static indeterminacy we are getting is 0. So it is the number of reactions are equal to the number of equilibrium equations. Then it is very easy to find out the number of reactions. Whereas when we see into the kinematic indeterminacy, so here we have 1 degree of freedom. Here we have 2 degrees of freedom. Right? So 1 plus 2 will gives me 3. So this beam is kinematically indeterminate with degree of 3. This is the one way. Or another way is directly substitute the formula, the values in formula, that is dk is equal to 3j minus r. So joints, we have 2 joints here, and number of reactions we are getting here is 3. So 6 minus 3 is 3. Right? This is statically determinate beam, but it is statically kinematically indeterminate. So now we can define the degree of kinematic indeterminacy as the number of additional equations necessary for the determination of all the independent components is known as degree of kinematic indeterminacy. As I said, here we initially, instead of finding out reactions, we will try to find out the displacements. From the displacement, we will find out the member forces. Okay. Now we'll see the different how to find out the degree of kinematic for beams, rigid jointed frames, and pin jointed frames, that is trusses. So this is the beam with both ends are pinned. Okay. So now we know how many reactions we'll get here. It is AX, AY, BX, and BY. Now the number of let us find out the degree of static indeterminacy. Number of reactions here we are getting 4. Number of equilibrium equations are 3. And the degree of static indeterminacy is number of unknowns minus number of equations. That gives me 4 minus 3, 1. Now to find out the degree of kinematic indeterminacy, the same formula we can apply here. Either we can use this formula method, or we can just find out how many degrees of freedom are there at each end. So first here, this is the pinned end. We have 1 degree of freedom because it is free to rotate with respect to this point. Same thing at this end also, we have a pinned end, so we will get 1 degree of freedom. So sum of 1 plus 1 gives me 2. Even we substitute the same value in here, 3j minus r, joints are 2, we have 2 joints, and we have number of reactions are 4. Here we have got, so 6 minus 4, 2. Okay, this is one. Let us solve a proper cantilever where one end is fixed, another end is roller. So at fixed end we have 3 reactions, whereas for roller we have 1 reaction, that is vertical direction. Now let us solve for statically indeterminate, degree of statically indeterminate. So number of reactions are 4, number of equilibrium equations are 3. So degree of static indeterminacy is number of reactions minus number of equations. That gives me 1 minus 3, 1. Now degree of kinematic indeterminacy is, here we have the degree of freedom, because this is fixed end, here degree of freedom is 0. Whereas for roller it is 2. Why 2? It is free to move in horizontal direction and it is free to rotate with respect to the z value. Okay. Now the degree of kinematic indeterminacy is 2. 0 plus 2 is 2. Let us solve using this equation. Kinematic indeterminacy can be found out by 3j minus r. Okay. So 3, number of joints we have is 1 here and 2 here. So 2 minus number of reactions we are getting is so 3 plus 1, that gives me 2. So let us solve find out the degree of kinematic indeterminacy for continuous beam where one end is pinned, one end is roller, another end is roller. So for pinned we'll get 2 reactions, that is in horizontal reaction, vertical reaction. Roller will get 1 reaction, and here also 1 reaction. Here the number of reactions here we'll get is here 1 gives me 4, and number of equilibrium equations are 3. Now degree of static indeterminacy is 4 minus 3, it is 1. Whereas for degree of kinematic indeterminacy here is, so let us see, for pin the degree of freedom is 1, for roller degree of freedom is 2, for here degree of freedom is 2. Okay. Now, sorry, it's a mistake. So the total number of degree of freedom we will get is 5. When we substitute the same here, so it is 3, number of joints are 3, minus number of reactions are 4. So that gives me 9 minus 4, it is 5. So this is kinematically indeterminate with a degree 5. Now let us see for a frame. So this is a frame, one end is fixed, other end is free. We'll first find out what is the statical indeterminacy of this frame. So how many reactions we are getting here? 3. Now the degree of static indeterminacy is 3 minus 3, that is 0. This is fine. Now let us see what is the kinematic indeterminacy. To find out the kinematic indeterminacy here, in this part, the degree of freedom is 0. Okay. Now here, the degree of freedom at this end is 2. And here also, the degree of freedom, sorry, here it is 3. Here the degree of freedom is, since this is known, so here also we'll get 3. Right? But here what we'll assume is, what is the assumption is that this frame is inextensible. What does this inextensible? So let us take a vertical cantilever. This is fixed. It has a node. Initially, it has the width of height of 3 meters. And after application, or I am pulling this, I am applying a load the opposite direction of P. I am trying to pull it at this node. Let us give the name here 1, 2. I am applying a load at node, and the beam is it is extending, and the change of length or the displaced length is coming like 3.1 meter. Some displacement is taking place, right? It is extending. Okay. What here we assume is inextensible. This is rigid. The beam is rigid. Even in the application of load, the change in dimension won't take place. The 3 meter will remain 3 after application of load. Either it is a compressive load or tension. This is for vertical. Similarly, for beam also, horizontal beam, we'll assume even if I apply a load here in both directions, we are assuming it is rigid. So if it is initial length is 3 meters, the final displaced length will also be 3 meters. There won't be any change in length. The same thing we assume here. And now if we do that, here since this is a free node, there is a no support condition, we assume that it won't have a vertical direction because of this. It is, since it is connected, this beam won't displace in vertical direction. So this one, it is like a support, simply supported. Similarly, it won't rotate. The beam won't rotate because it is rigid. It is fixed. This condition will acting as fixed. So -1. Now when we apply a load here, something like that. So since we don't have any support condition here, this will move. This will move, causing a deflection here. So x direction displacement will be there. Same thing here also. Here, this, since this is free, it is free to rotate in vertical direction. It is free to vertical direction, horizontal direction, and it is free to rotate it. So now the sum of this will be, here we have 3 degrees of freedom, and here we have 1 degree of freedom. So the 3 plus 4 gives me 3 plus 1 gives me 4. So the degree of indeterminacy is 4. If they don't mention that this frame is not rigid or inextensible, then the number of degree of indeterminacy will be 6. 3 plus 3, it is 6. Okay. This was based on the conceptual theory. Now let us try to apply the same in the formula. So for the frames, this is the formula here. Okay. In the formula, if you remember, it is the easiest way to solve this. That is, we know number of joints we are getting here. 1, 2, 3. We have 3 joints. Joints are 3. How many reactions we have? 3. How many members? M is nothing but number of members. So we'll need to count. Members are 1, 2. So number of members are 2. So when we substitute that, we'll get value as 4. Assuming that it is inextensible or rigid. If we assume it is extensible, what we need to do is there is a slighter modification of this formula. We need to remove this m. Okay, when we remove that m, then dk will be equal to 3 into 3 minus 3 is 6. I hope you understood this. Okay, so you need to make sure that whether they have mentioned whether it is extensible or inextensible. If it is inextensible, you need to add this minus m. You need to subtract with. If it is extensible, then you no need to add this minus m. Now let us take another frame where we have the support on the other end. The same thing here. Here, if we take at the fixed end, we have 3 reactions: AX, AY, MA. At this C point, we have 1 reaction. So now the degree of static indeterminacy is number of reactions minus number of equations, that is 4 minus 1. It is statically indeterminate frame because of this extra support. And what about the degree of kinematic indeterminacy? So this is the formula of degree of kinematic indeterminacy. We assume that while solving all the problems, we assume that it is rigid, the frame is rigid or inextensible. Okay, so now we'll substitute this m here. The same thing, number of joints we have is 1, 2, 3, and number of reactions we have here is, here we have 3 reactions, here we have 1 reaction, 3 plus 4, it is 1, and number of members are 2, 1, 2. Now the degree of kinematic indeterminacy is 3. It gives me 3. To understand it conceptually, initially we got here we have 1 degree of freedom. Okay, but whereas here we initially had 3 degrees of freedom, but it is preventing in the movement in vertical direction. So here we have 3 degrees. For roller we have 2 degrees of freedom. Right? The same thing. When we substitute the 1 plus 3, 2 is 3. Let us see another problem. This is a full frame. Okay. Here we have 3 reactions. Here also we have 3 reactions. The number of reactions are 6. It is statically indeterminate with the degree of 3. And the kinematic indeterminacy, same, we assume that it is rigid or inextensible. And when we substitute these values, we have how many nodes we have here? 1, 2, 3, and 4. 4 nodes we have here. And how many members? 1, 2, 3. 3 members we have. Substituting these values, it will end up 3. How 3? Let us understand its concept. Here we have, as I said, in x direction it is free to move. It is also x direction it is free to move. Right? It's come 2 And because of this movement, at this rotation, there will be a rotation. Okay? Because this both nodes, we don't have any of the what we call support conditions. If those are free, they are just, we assume it is rigid, and we assume that it is theta A will be rotation takes place, theta B rotation will takes place, and here we'll get theta A, theta B, and x in at node 2 and x in node 3. Since we are assuming that it is rigid, the displacement at node 2 is equal to displacement at 3. So that is x2 equal to x3. Then how many degrees of freedom we are getting here? Theta A, theta B, and x in a horizontal direction. Right? That hence we will get 3 degrees of freedom, since degree of kinematic indeterminacy is 3. Let us see the find out the degree of kinematic indeterminacy for this frame. We already have seen this in the previous video, how to find number of reactions. So here, since the additional member is coming, we'll get internal indeterminacy 2, external indeterminacy is 3, whereas internal indeterminacy is nothing but 3 into number of loops. Loops in the sense the closed form. This, since it is closed, there is no opening, so we consider this one as, since it has one opening, this won't be considered as loop. Okay. So the internal indeterminacy also, it's 3. The total static indeterminacy here for this is 6. Now let us find the degree of kinematic indeterminacy. The formula is same. We'll substitute number of joints. How many joints we'll get here? So we have 1, 2, 3, 4, 5, 6. 6 number of joints are there. How many number of reactions? That is also 6. We know. Now number of members: 1, 2, 3, 4, 5, and 6. When we substitute these values, 6 nodes and 6 members and 6 reactions, so the total we'll get is 6. If it is inextensible and rigid, then the kinematic indeterminacy is 6. Let us see for truss. This is a truss, statically determinate truss. We have seen this. This is pinned end, this is roller. Here we'll get 2 reactions, here we'll get 1 reaction. Number of equation is 3. So degree of static indeterminacy is 0. Here also, similar to frame, we need to take internal indeterminacy, and it is given by m minus 2j plus 3, 2j plus r. Okay, so here we have 3 nodes, 3 members, 1, 2, 3. Number of joints are 3, 1, 2, and number of reactions are 3. Substituting it, 0. Okay. Sum of the degree of static indeterminacy is nothing but sum of external indeterminacy and internal indeterminacy, that is 0. For the truss, the degree of kinematic indeterminacy is a kind of simple. You just need to use this formula 2j minus r. Here in the pin jointed truss, we assume that we have only 2 ways of movement, that is x direction and y direction. And number of joints we have here is 3 joints. 2j is 2 into 3 6, and number of reaction is 3. That gives me 3. So it is kinematically indeterminate. So let us see another truss. This is statically indeterminate truss. At pin end we have 2 reactions. So here also it is pin end. Externally it is statically indeterminate, as well as internally also it is statically indeterminate. So it is statically indeterminate to 1, and internally it is indeterminate to 1. Now what about the kinematic indeterminacy? So here dk is equal to 2j minus r. So number of reactions we are getting joints here we have is 4, that is 1, 2, 3 and 4. And how many members we have here? Here we notified the members. So number of reactions are, so G, the kinematic indeterminacy is 4. So this was something about static indeterminacy and kinematic indeterminacy. This is the summary table which is useful for remembering all these formulas. So I have divided it like beams, rigid jointed frames and pin jointed frames. If it is statically indeterminate, then the formula is reactions minus 3. And if it is kinematic indeterminate, it should be like 3j minus r. For rigid jointed frames also, the statically indeterminacy is r minus 3. This is external. Okay. Whereas internal is, if we have additional member like closed loops, then we need to add this 3c. This will give me, this is the total degree of static indeterminacy. Whereas for kinematic indeterminacy, if it is extensible, the formula is only 3j minus r. If it is inextensible or rigid, then it is 3j minus r minus m. Similarly, for pin jointed frame also, external indeterminacy is nothing but, static indeterminacy is nothing but r minus 3, and internal, if we consider this internal indeterminacy, then it should be m plus r minus 2j. Right? And here, this is the overall static indeterminacy. Same thing for kinematic indeterminacy. If it is extensible, it's just 2j minus r. If we assume that this is also rigid, then we add, then subtract the number of reaction from this form. Okay. Hope this is clear. See you in the next session. Thank you.